organizers who invited me to talk here. And it's nice to come back to ITAMP and Cambridge. So it's beautiful. Today I would like to examine the possibility of directly laser cooling of lanthanide oxides. So these molecules are interesting for us because fascinating kind of electronic structure, very large magnetic moment, and anisotropic properties. I just mention a little bit. Of course, many people know that lanthanide series is located at the bottom of the periodic table, and they have that kind of unusual property that all lanthanides atoms have the same outer shell. It's a 6s2 filled shell. But under this shell, they have 4f electron shells, and for some atoms, those shells are not filled. They're open shells. And most often, f electrons have unpaired electrons kind of properties, and it creates a large magnetic moment. And if you see on this series on the graph, these letters actually describe non-zero angular momentum for these atoms, which actually most important to create anisotropic properties. So, and it's very obvious from this graph that there are some lanthanides, heavy lanthanides, have much larger magnetic moment and also angular momentum. So we're actually interested in this kind of lanthanides. So I just want to also add that lanthanides and their components are actually very interesting for technologies and science. They have, as they call, unfilled F shell, rich variety applications, and of course I will mention it in, as optical elements, as the catalysis, electronics, sensors, life science, single molecular magnets for spinotronics. One of the latest interest studies. In all these applications, orbital anisotropy is crucial. That's why they are used. So, but before going to molecules with lanthanides, I would like to emphasize, actually it's from a first point of view, it's kind of little bit brave to go there because even atoms have very busy and a very complex spectrum. This is an example of erbium atom. Ground state, some excited states I used to actually experiment. So, and it seems that spontaneous emission down during these laser cycles, like cooling cycles, will break everything. It's impossible because many molecules will be lost by this kind of emission going down to all sorts of states. But apparently, there are some ways to cool this kind of molecules, and we know examples like erbium, dysprosium, holmium, thulium are really perfectly cooled, and they have nano-Kelvin even temperatures. So what happened? How it could be happen? Apparently, there's a beautiful observation and investigation have been done with erbium, particularly cooling, laser cooling by Mike Leland from NIST and ST in his experiment, and he found that because of the large magnetic moment for these atoms, so those atoms that actually fell out of the so-called cycle, laser cycle, they're not leaving trap. And they kept by quadruple magnetic moment in the mode and remain in vicinity, and then eventually cascade to the ground state and participate again. So this is nice property. Its magnetic moment, specifically for lanthanides, really play a big role, and hopefully, I cannot guarantee right now, but it has to be investigated whether it will play a role in molecules as well for cooling. So my talk has two parts. First part, I would like to explore erbium-OH and erbium-O, so oxide molecules, on likelihood of direct laser cooling. For that reason, we look at the geometry optimization. We also calculated potential services for ground-excited states, Frank-Condon factors, magnetic and dipolar properties. So I also, in principle, very much interested, and I will do again and again to look at it, how 4F electrons actually participate, because in the past it was sort of idea, maybe far away past, that 4F electrons actually do not participate any coupling, any chemical reactions, because they are much lower below the surface, the outside of valence shell. But apparently it's not exactly true, and we can analyze it. So the second part, if I have time, I was interested as well attaching optical cycling center to functionalized fullerene. When we embedded lanthanide molecules inside, there are very interesting properties of it. It's amazing, actually. And in this case, when these lanthanide molecules inside of fullerene, they actually lose a lot of electrons to the fullerene surface, and they are left along as highly charged ions, but they still create molecule, which is totally impossible, right? But it is possible, and it was actually already shown that this could happen. So, and then I mentioned a little bit, so how to, maybe this kind of system could be cooled with OCC. So I'm not going to read all these things. I just mentioned that we use density functional theory. We use time-dependent density functional theory. We also use SF, mol-pro suit, with and without spin orbit. We are thinking about using Dirac, but it didn't happen yet. It's even more sophisticated, have to do. So we used effective core potential, or even calculation all electrons included, full electron calculation. So this is a very conventional graph. The only thing I would like to emphasize here, so if we compare erbium OH with very classic already calcium OH, strontium OH, so there is a difference in the electron distribution. So we found the lowest ground state, and there are many. It's a ground state actually not state, but it's a configuration. There are many states belong there, but they're all ground kind of, from my point of view. So you can call it X. And the lowest one, it's quartet sigma. And it's linear geometry, indeed. But nevertheless, we can see that ionic coupling, the 6s electron going to oxygen, not totally leave atom. So, but it's not maybe terrible. So we will see later. I will discuss why. So, yeah, here I tried to mention it. Apparently, we found that 6s and 6p excited electron. They actually have wave functions pretty similar shape. So they kind of react to ligands the same way, and therefore Frank-Condon factors is extremely good. So here we look at sort of orbitals, homo-LUMO, traditional kind of way, and we can see, so the rest, 6s electron, which actually left, pretty concentrated around the sort of core of erbium. And I assume that there's some contraction going on with 4f electron. For ions, 4f electrons normally going even collapse a little bit. So 4f electrons not really overlapping with ligand. So he is excited, different kind of states, excited 6p, it's, I would say, A pi state for optimized geometry, and they also behave positive way. So just a little bit before going to electronic structure results. So remind you for erbium, so what we have, it's relativistic atom. It has two relativistic subshells. And assuming, normally it's assumed that for F5 halves, it's a closed shell. J equals 0, actually. But the outer shell for F7 half, it has two electrons which are unpaired. And those electrons responsible for this quite high magnetic moment. And of course, OH has one electron unpaired, and of course, that's how they interact mostly. We use tensor analysis, but I'm not going to talk too much about it because all these interactions in isotropic interactions very important in this, for description of this kind of systems. Otherwise, it's too complicated. So this is actually what I called ground configuration. So there's no excited state here, right? I didn't put it there. So it means there's a different kind of coupling. There's a covalent coupling and very ionic couplings between erbium and OH. And in this case, a calculation does not include spin orbit. Here we include spin orbit, a big difference, of course. But what we see, there are sort of bands, right? Still bands, some kind of different potentials, few hundred no, maybe a little bit less, but split.
This is a message from Advanced Health. The following is an important.
Terrible. Watch is dangerous, actually. It all the time tells me what to do. So you maybe wonder what kind of what splittings, what about? So all these potentials, here's a little split, but if you look at the different scale, of course, it's significant difference. So they all actually going to the same limit on the long range, and those the same, but the difference between those is orientation of F electron. So for each of these band of electron has different orientation, and of course you can describe it certain notation and different formula. So, but then apparently spin orbit is so big, so we can see more this kind of bands appear. So, okay, it's complicated. But then here I show green. It's excited states also had bands, of course. Why not? And they also have all these anisotropies, interactions. So, but here's the lowest one, and I put it there. And this excited states, it's amount all this F electron kind of structure. So, and dipole moment between lowest and lowest here, whatever, you have to choose omega. Omega is a projection, total angular momentum on the axis of molecule. And for lowest band, we have all sort of omegas from like 9 or 8 omegas. And here too. So the omega could change 0 or 1, not more. So you have to really show this, whatever it's supposed to be, transition. But what is interesting, I believe, this transition is very strong. It's like 3-4 atomic unit strengths. But all transition between those, from here, that I don't know, we didn't check, we should probably check this kind of transition. But in principle, transition between states which belong to ground configurations is very weak. The strongest is 10 to minus 3 order of magnitude only, and -5 and very low, and sometimes it doesn't exist. So Frank-Condon factor is very high, as I told before. So we'll go to next one, monoxide. And we didn't expect it has also a strong Frank-Condon factor. Obviously, there's no hydrogen molecule to take some part of p electron, but apparently it's not really ionic coupling, because if you look at permanent dipole moment, it assumed if it's totally ionic coupling, it should be like 14 dBi, but it is not. So our calculation shows. So it's a unique kind of bonding, and it's probably was in previous molecule. Dative, call it bonding, both covalent and ionic. But here it's actually much stronger part of the covalent bonding. And then this in covalent bonding, there are several electrons participate. Sort of they moved out of erbium core and somehow participate interacting with oxygen. P electron. So, but this rest of success still there around core, and the same excited states, mostly located around the core. Here's bonding orbitals. I know how much you can take from there, but there's a d electron present because F moved to the d. So there is some kind of distribution of this natural electron configuration. So, but again, we can see in this kind of transition, Frank-Condon factor is very high. Again, because of shape, very similar shape for successes XP, and then when cycling happened, wave functions pretty similar, and that what happened. 5 minutes, okay. I talk about lanthanides. I may not even. This is our recent paper when we suggested to attach OCC center in order to cool fullerene, and fullerene is amazing system, and I probably should not talk about too much, but it is empty and very symmetric, especially these two fullerenes, and it's require interesting investigation because this symmetry changes all rules and transitions if it's within fullerene. But we sort of interested in embedding erbium atoms inside of fullerene, and apparently both atoms move 6 electrons from erbium to surface of fullerene. A red color shows those carbons which are affected by this interaction with erbium. But remaining sort of cores left purely F core, 4 F cores, 11 kind of electrons on it. And then further investigation on the spin densities shown these two ions actually bound together, where this electron shown with green and the blue things that erbium plus 3, and that electron came from some kind of F shell, and the bonding is along one of the axes of fullerene, and there is an experimental paper, recent, confirmed this bonding possible, but it's a different kind of, not fullerene at all. It's a very complex legend. So here's one of the last almost slides when we try to attach optical cycling center with a link, which believe this is very nice link, which kept the optical cycling center linear without bending towards this big surface. So maybe interesting that magnetic moment on this system inside is a 13 Bohr magneton, and huge permanent dipole moment now with all this together. So, and in conclusion, I just say we still working on it, interested, and because the levels of lanthanides, lanthanide molecule, or even atom inside the fullerene, they could have so-called Kramer doublets, which is only possible for this kind of systems, because they degenerate kind of states, which become lifted degeneracy only under influence of a ligand field, but it cannot be lifted by magnetic field at all. It's like parity preservation against reflection of wave function through some plane when the wave function could change sign. So that is very interesting. And of course, there are many of them. I just show, like here, for example. So there are many of them. So you can choose. There's the lowest one or highest one. So first of all, embedding these qubit type things actually inside of fullerenes, protecting them from environment. And then we sort of now looking at how chain them together and even cool them. Of course, one by one, but in principle, I think it's an interesting way to go to use these amazing, beautiful molecules and atoms of lanthanide series. Thank you very much.
Really interesting talk. So have you checked that the actinide fluorides act basically the same way as the actinide hydroxides?
No, no. Yeah, we should, of course.
Yeah, I mean,
Yeah, yeah, we need just something to attract electrons. Of course, it could be maybe even better, yeah.
yeah. Well, then my follow-up to that is, I'm going around telling people that silver is the laser coolable fluorine.
Yeah,
Really high electronegativity.
yeah, silver is similar, but not as strong maybe, right?
Yeah,
A little
not
bit.
strong, although I've been kind of shocked at just how ionic the bonds are.
Yeah.
Or at least how big the dipole moments are.
Well,
for
as a
alpha
theorist, I would say calculate the molecule even complex with ionic bonding is much more easy because correlation effects are not as important if when covalently bound systems. So ionic bonding is an amazing kind of things. You can really play with it.
Can I ask about like the plots with many lines? Like,
We go back.
yeah, this is like super daunting to me, but also
Yeah.
it seems like it could have been much worse. You get all these crossings that don't seem to be avoided.
No, they are very
And not here, but I mean with the
parallel. Not parallel, but yeah.
yeah, but I mean with the covalent states, this seems to
Oh, yeah, that one.
kind of cross without
Yeah.
this being avoided. Is that
Yeah, it's a conical intersections,
Is
I
it?
guess. You can ignore it or not. Yeah, we're now working on this kind of. We want to dissociate strontium OH on OH and strontium using Feshbach resonances. That's exactly coming, this kind of problems. So, yeah.
Svetlana? So you said something like there are many possible ground states and it's like you can pick which one you like, but shouldn't there be just one ground state?
No, I mean, what I already said, this kind of potential or band even have different orientation of F electrons. They have all rights to orient. They have this freedom. So how you, maybe it would be nice to forbid some orientations. I don't know how we can do this. Then you can restrict number of these
But so
things.
each one of
But they are
these-
very, I mean, look at how far away. It's scary, but if you look, it's 10, 5,000, few hundred even.
So there are no transitions between these bands. Those are
Very low transitions, low intensity, right? So, it's still allowed. If you really like it, we can find some levels that dipole moments like 10 to -3 atomic units. It's actually possible for modern lasers, I believe, right? So if you need, for some reason, to do these things.
I was curious. It seems like recently there's this, I don't know if I want to call it conventional wisdom, that if you want to cool benzene, just put a bunch of fluorine on it, and the Frank-Condon factors get better. Is there any, like, hi, Divine.
I won't call it wisdom.
Divine thinks
That's
to think
recent
that if you
wisdom.
put fluorine on it. Is there any, like, equivalent kind of wisdom or Divine's thoughts on improving the Frank-Condon factors for these fluorides molecules?
Oh, not about this system at all. You talk about.
No, about
sorry.
fuel C60.
Yeah, if I wanted to
C60.
make the C60 Frank-Condon
Oh,
factors better,
oh.
can I functionalize
Uh-huh.
little fluorines, or is there any, like, emerging wisdom?
Yeah. No, I think it's a big problem, but it's not only my problem. It's a problem with UCLA people who are actually also promoting huge molecules cooling with these optical cycling centers. And I believe sometimes we can see, in experiment how much they cool actually, because it looks nice. And if you look, optical cycling center totally independent on this big molecule attached to this, and behave perfectly well. Really, Frank-Condon factor is 0.97. So, but what about this huge molecule next to it? How cold it is? I don't think it's done. Maybe Eric somewhere, Eric. Anyway, so it would be nice to sometimes to understand. It's because of so many new ideas about it. And it's practically solve any problem for any big molecule. No problem attached, right? So, but how much you cool these things? Yeah, that's going to be important.
Will it eventually become a limitation if it's uncoupled? If you want to actually extract vibrational energy from the thing you're trying to cool, is the decoupling of the optical cycling transition and the giant molecule that you have going to be a limitation at a certain point that can no longer?
Yeah, attachment changed slightly, of course, molecule, big one. But I don't know yet. I like fullerene because it's so symmetric. It just, I think I can deal with this. If you look at single molecular magnets, when they attach all sort of huge kind of system, it's scary for me, of course, not chemist. So, but we'll slowly maybe understand better of this kind of.
I just have a quick clarification. Sodium plus OH minus, I think you're trying to sort of emphasize that this is an ionic bond.
Yeah.
Ion pair is way up there somewhere, right?
Go higher. Huh?
Yeah,
No, no.
yes. Okay, so
Oh, opposite direction.
no, it was,
H.
no, it's fine, it was
No,
just
no,
a
no,
clarification. So let's thank Svetlana.
Oh. Thank you very much.